name is Muhammad Shafiq Ahmad bin Abdul. Okay, now I will like to talk about introduction of the radiation. Okay, consider a hot object that is suspended in evacuate chamber. Those walls are at the room temperature. The hot object will eventually cool down and reach the thermal equilibrium which its surrounding. So this mechanism we call it by its radiation. So radiation transfer occur in solid as well as liquid and gases, but heat transfer through the evacuated space can be occur only by the radiation. For example, the energy of the sun reaches the earth by radiation. The theoretical foundation of radiation was established in 1864 by Professor James Clerk Maxwell, who postulated that accelerated change can changing electric current give rise to electric and magnetic field. This rapidly moved field are called electromagnetic wave or electromagnetic radiation. Electromagnetic waves are characterized by their frequency or wavelength. These two properties in a medium are related by where to lambda equal to c over v, which is c is speed of propagation of a wave in medium, lambda is the wavelength, and v is the frequency. The speed propagation in a medium is related to the speed of light in a vacuum by c equal to c naught over n, which is c is the speed of light and n equal to the index of the refraction of that medium.
Hi and Assalamualaikum. My name is Syed Muhammad Zulfahmi bin Syed Zawawi and my metric number is BDA30603, and I will be explaining about the black body radiation. Black body radiation is a perfect emitter and absorber of radiation. A black body absorbs all incident radiation regardless of wavelength and directions. A black body is a diffuse emitter. Diffuse means independent of directions. Another type of body that closely resembles a black body is a large cavity with a small opening. As you can see from the picture, there is a small opening of area A and is considered as black body radiation. Black body. Okay. In 1884, by Ludwig Boltzmann proposed a law called Stephen-Boltzmann law, and EB is called a black body emissive power. He said the emission of thermal radiation is proportional to the fourth power of the absolute temperature. The equation is E in bracket T is equal to sigma T to the power of 4, where sigma is equal to 5.67 multiplied by 10 to the power of 8. It is the Stephen-Boltzmann constant, where T is the absolute temperature of the surface in K. The Stephen-Boltzmann law gives the total black body emissive power, EB, which is the sum of radiation emitted over all wavelengths. Sometimes, we need to know the spectral black body emissive power, which is the amount of radiation energy emitted by the black body at an absolute temperature T per unit time, per unit surface area, and per unit wavelength about the wavelengths. The relation for the spectral black body emissive power, EB, was developed by Max Planck in 1901 in conjunction with famous quantum theory. This relation is known as Planck's law and is expressed as E in bracket lambda T equal to C1 over lambda to the power of 5 in bracket exponent in bracket C2 over lambda T minus 1, where C1 is equal to 2 pi Hc and C2 is equal to Hc over K. Okay. T is the absolute temperature of the surface, where lambda is the wavelength of the radiation emitted. while K equal to 1.3065 multiplied by 10 to the power of 223 is a Boltzmann constant. This relation is valid for a surface in a vacuum or a gas. For other mediums, it needs to modify by replacing C1 by C1 over N2, where N is the index of the refraction of the medium. Note that the term spectral indicates dependence on wavelengths. This figure shows the variation of the black body emitting power with wavelength for several temperatures. You can see as the temperature increases, the peak of the curve in figure shifts towards shorter wavelength. The wavelength at which the peak occurs for a specified temperature is given by Wien's displacement law. The equation is lambda T equal to 2897.8. This relation was originally developed by Willy Wien in 1894 using classical thermodynamics, but it can also be obtained by differentiating Planck's law equation with ratio to lambda while holding T constant and setting the result equal to 0. A plot of Wien's displacement law, which is the locus of the peaks of radiation emission curve, is also given in the figure before. The peak of the solar radiation, for example, occurs at lambda 2897.8 over 5780 equal to 0.5 meters, which is near the middle of the visible range. The peak of the radiation emitted by a surface at room temperature T equal to 298K occurs at 9.72 meter, which is well into the infrared region of the spectrum. As you can see, the figure shows a surface that reflects straight while absorbing the remaining parts of the incident light apparent to the eye. Okay.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hamid bin Mutazari with number BDA30603. For radiative properties, the radiation is considered to be a surface phenomenon, which is emissivity, absorption, reflectivity, and transmissivity. For emissivity is the ratio of the radiation emitted by the surface at a given temperature. There were four emissivity, which is spectral directional, total directional, spectral hemispherical, and total hemispherical. The formula for spectral directional is strain lambda equal to I lambda divided by IB lambda. For total directional, strain theta equal to IE over IB. And for spectral hemispherical, the formula is strain lambda equal to E lambda over EB lambda. And for total hemispherical, strain equal to E over EB. The next is absorption. Absorption is fraction of irradiation. Can be calculated by absorbed radiation divided by incident radiation. And the next is reflectivity. Can be calculated reflectivity is a fraction reflected by the surface. Can be calculated by reflected radiation divided by incident radiation. And the last is transmitted, which is fraction that is transmitted, can be calculated by the formula transmitted radiation divided by incident radiation.
Hello, my name is Muhammad Hamid. So right now we will move on to the question 1, which is the electromagnetic spectrum that lies between 0.40 and 0.67 amps. What is called visible light. Within the spectrum, the color violet has the shortest wavelength, while the color red has the longest wavelength. So we need to distinguish of these colors, violet or red, to get more potent energy. So for these questions, there are a few steps to solve this equation. So we move on to the first step, which is firstly we need to assume that the medium is L. So the index of the refraction is 1 and it's able 12.1. So the wavelength ranges of the different colors. So the wavelength of the violet color is as follows, which is lambda equals 0.40. So for the next step is we need to compute the speed of the propagation of wave in the air by using the following formula, which is CL equals C naught over N, which is CO is the speed of light and N is the index of the reflection. So we need to substitute the 2.9979 times 10 to the power of 8 for the C naught and 1 for the index of reflection, which is we call 2.9979 on 7. So we substitute C naught and N to the and we got the CL, which is 2.9979 times 10 to the power of 9. Okay. I'm sorry, 10 to the power of 2. So we move on to the next step, which is we need to compute the quantum energy of electromagnetic wave in the air by using the following formula, which is E HCl over lambda, which is we know that lambda is the wavelength of electromagnetic wave and H is the Planck constant and Cl is the speed of wave propagation in air medium. So from this formula, and we got all the value for H, for the CL and for the lambda. So we substitute all these value into the formula and we got E equal 4.966 times 10 to the power of negative 19 joules. So the total energy of the violet color is 4.966 times 10 to the power of negative 19. So right now we got the total energy for the violet color. So for the last one we need to find for the red color. So for the next step, which is we know that the lambda for the red color is 0.76. So we need to compute same step as the violet, same step as we find the violet color. So we use the same formula, which is HCl over lambda. So we know that the value for the H, the value for the CL and the value for the lambda. So we substitute in the equations and we can get the volume of the E, which is 2.6137 times 10 to the negative 90. So the total energy of the red color is 2.6137 times 10 to the power of negative 90. So as we compare, we know that the total energy of the violet color is propagate more light more than the red in color. That's all. Thank you.
So, Assalamualaikum warahmatullahi wabarakatuh. My name is Aneh. Trigonometry BDA30603. So I will explain about the questions. Given the questions, an electromagnetic wave with a wavelength 0.5 is being propagated in the different medium, which is we have three: air, water and glass. And if given the refractive index of the water, air and glass, the 1 for the air, 1.33 for the water and 1.5 for the glass. So in this question, we must determine the photon energy of three medium. So we get from the table 12.1, we get the lambda 0 is equal to 0.4 millimeter. So we assume for each medium in the refractive index form, and assume the electromagnetic wave is the visible positions consists of visible color. So to get the photon energy, we must calculate the speed of propagation of wave. In this question, CO is the speed of light, and we get 2.998 to the power of 8, and N is the refractive index, is equal for the A is equal to 1. So we substitute CO and N in the formula. So we get the CA is equal to 2.9979. So the speed of propagation of wave in the A, we get this. Other than that, to calculate the next medium, which is the A. No. This is the C, speed of propagation. So next we must to calculate the photon energy, which is this is the formula. E equal to HCA per lambda. So we got the H is equal to 6.63 to the power of 34, negative 34. So we substitute all this value in the formula. 6.626 to the power of negative 34, which is the H, and this is the CA. This is lambda. This is equation formula. So we get the E, photon energy of electromagnetic wave in the air, is equal to 3.1 eV. So the next medium is the water. So we compute the speed of propagation of wave in the water using the same formula, which is this is for the light, and this is the refractive index for the water given by the questions. Given by the question, N is equal to 1.33, and we get the speed of propagation of wave in water 2.2254 to the power of 8. And when we get this speed of propagation water, substitute into the formula of photon energy of electromagnetic wave in the water. So we get the photon energy is 2.3 eV. So the same step for the glass, compute the speed propagation of wave in the glass, which is this is the formula. Then we get the speed of propagation of wave is equal to 1.9986 to the power of 8. And this is the refracted index given by the equation, which is 1.5, and substitute into the formula. Then we get photon energy of electromagnetic wave in the glass is equal to 2.066. So when we calculate all the value of the photon energy, we get the photon energy of air is the most value compared to the water and the glass. So that's all for me. This is the question for the